Good afternoon, everyone. It is my immense pleasure to welcome all the partakers on the behalf of Creators Garage and Computers Club to the last day, that is day 6 of our DSA Bootcamp. Thank you all for taking your time off from your brisk schedule and being a part of our bootcamp today. It is a delight to have you all today with us, and special thanks to our speaker, Mumal Rathore. Hope you all are ready to learn and gain from today's lecture and learn about some hashing topics on DSA. It is a great opportunity for us all to listen to Mumal Rathore ma'am and explore more about today's topics. Mumal Rathore is a coordinator at Computers Club SGSITS. She has been a mentor in many ventures of the club aiming to train enthusiasts with tech skills. She is currently a trainer at Volkswagen University program. All your queries will be answered here only. So please stay tuned with us throughout the whole session. Hope you also learn very much from our past lectures. So without any further ado, let's get started. Over to you, ma'am.
Thank you. Thanks a lot for the sweet introduction. And as you said, without any further ado, let us get into the thing that we came here to learn. So let me start sharing and let me know if my screen is visible to you. All right. So before we begin with hashing, I would like to give a short introduction to what this topic is and why it is so important that we had a separate day for hashing. So hashing does not come by default into data structures that you learn, but it is rather a technique that you use to use the data structures more efficiently. So there may be questions which you could solve using existing data structures, the data structures that you have learned until now, but using hashing, you could do so with more ease and more efficiently, while cutting down on time complexities and space complexity as well. So, which is why hashing is a very important and very easy data structure to know and a technique to practice as well. So it's a very neat code, nothing too complex about it. And in fact, in interviews as well, there are many questions that get thrown around about the concept of hashing. So, from that perspective, we are first going to cover some important concepts of hashing, what hashing is, what are hash tables, hash functions, and everything. And in the second half, we are going to look at some questions in which hashing is a very efficient approach which you could use to solve the questions, right? So, let us begin with what actually is hashing. Hashing in the data structure is a technique of mapping large chunk of data into small tables. And for that purpose, we use a hash function, right? So what hashing does is that whenever you have a very big data set, or for example, an array which has thousands of entries, and you want to store all of that data efficiently into a smaller data structure, you use hashing. And it also says that hashing uniquely identifies a specific item from a collection of similar items, right? And to uniquely identify an item, what we need is an ID, thing like an ID which you can give to a specific item, and then you can use that ID to identify every single item, right? So this is what hashing does. Using the hash function, you actually extract or generate a unique ID or hash code for each of your entities from a collection, right? And then you can use that hash code to identify it specifically. So let us try to understand this with an example. Here we have some values, some input values, and we are going to use a hash function and to generate some keys, right? So what we want to do is, whenever we are solving, for example, a programming question, we have an array which can have many numbers, and each number has some constraints, right? There can be a constraint like the number of array is from 0 to n, where n can be a 9-digit number. If it is an integer, then it can be a 10 to the power 8 number, anywhere in the range from 0 to 10 to the power 8, right? So what happens is, if you want to store these values such that you can access these values in the time complexity of 1, so what you could do is, you could store these values in an array at the index. So that is called as open addressing. So if I have an array, and in the array on the 7th position, I store this value 7. On 16th position or 16th index, I will store 16. And on 33rd index, I will store 33, and so on, right? So in that way, I would need an array which has at least 43 elements supported, right? So if an array supports it, if an array can store 43 elements, then only it would be a good idea to use an array to directly search these items with a time complexity of 1, right? Otherwise, I would need to calculate, I would need to do a traversing on the array, or maybe I could use binary search, but that again would take a time of a logarithmic complexity, right? But not a constant time. So that is why we have hashing. In hashing, what we do is, we don't need a array as big as 43 to store these few entries. What we do is, we use a hash function. So what hash function does is, whenever you operate a hash function on a particular value, it is going to give you an output as a key. So for example, you have a h as your hash function. So this is your output key. And what it does is, here we are using a hash function as modulus function, right? So what we do is, on the given value, we apply a mod function. So for example, let us look at 7. 7 is our value. We apply the hash function on 7, which is 7 mod 7, and the output of this gives us the key. So our key becomes 0. Similarly, for 16, 16 mod 7, we get 2, right? And so on. So for 33, we get the key as 5, and the for 42, we get the key as 6. So now we can use these keys in an array to store our input values, right? So here we have stored at 0, since the key for 7 turned out to be 0. We stored 7 at the index 0. Then for 16, we again applied the hash function, and it gave us the key as 2. So we stored 16 at the second index, and so on. So now that you see that, if you are using a function like mod, so in our specific case, there can only be these 6 possible values, right? So these 6 possible keys can only be generated using mod 7 function. And now in this particular table, we can store all of our values, and then we can retrieve them using a time complexity of only 1, right? So it is going to have a time complexity big of 1. Now, why exactly do we need hashing? We could also do it using a direct array, right? So we could store 7 at the index 7 and 16 at the index 16 itself, and we didn't even need to apply this hash function. So why we need to do that is, suppose if we used a direct addressing for this, for storing this particular these particular values, then we would be needing an array of size 43 to store these elements. But with hashing, we can do so with only 6 elements, right? A 6 sized array. So that is a huge advantage of using hashing over direct indexing or regular arrays. You don't need to have a very large piece of memory to store your data. You can do so in a condensed manner, right? So to introduce this concept to you formally, let us look at some basic definition. So a hash table. This is generally asked in interviews. What is a hash table? So hash table is one of the implementations of hashing concepts, right? And in general, it is a simpler notation. It is a generalization of an array, right? So in array, what you do is, you have an index, and then in that particular index, you store the value directly. So that is called as direct addressing. So for example, if I have a value 42, then I would store it at the index 42, right? 42nd index, I will store the value 42. And if I have a value of, let's say 101, then I will store it at an index of 101, right? So that is called as direct addressing. But in hashing, what we do is, instead of directly storing the value to the index, we first apply a hash function, right? So using a hash function, what it does is it cut down on your memory required. So, for example, in our previous example, we saw that instead of having to use an array of 43 size, we could do so using only an array of size 7, right? So, hashing cuts down on the required space. Now you are able to afford, because with direct addressing it is not always possible to afford to allocate an array that can have a position for every possible key, right? Because in direct addressing, what happens is that the maximum limit that you have for your elements, for example, if an element of an array could be from 0 to 10 to the power 6, right? Then you would need an array of elements of which have every possible index from 0 to 10 to the power 6, right? And that isn't possible in general case. But with hashing, you could use a hash function, and it could give you some keys which you could use to store the same values in a very smaller chunk of memory, right? So this is the biggest advantage of using hashing. And since it works just like direct indexing, it can retrieve any element at the cost of only one, right? A constant complexity. So now this second para is saying the same thing, that if you want to store all possible keys, if suppose you wanted to store all the 10 to the power 6 keys, then you it would be a good idea to use direct addressing, because then all of the space would be needed to store all the keys, right? But if you have only a handful of numbers which range from 0 to 10 to the power 6, then it is a much better idea to use hashing, because it would save you memory and time. Now, hash functions are the functions that are used in hashing to get the keys, right? So you apply a hash function on your values, and then your keys are generated. So those keys you use to store the values and find them out. So this was the basic concept of hashing. Now there can be a drawback of hashing, which is called as collision. So collision happens when two keys map to the same hash code. So for example, in our slide we saw that we had a value 7 and we stored it at an index of 0, right? Then we had a value 16 and we stored it at second index, and so on. Now what if I had a value 35, right? So 35, after applying the hash function, 35 mod 7 also gives 0, right? So but since my 0th index is already occupied by 7, I do not have the space to store another value, right? So this is what is a collision. Collision happens when two values, after applying the hash function, give you the same key, right? So then your place is already occupied, and now you cannot store another element here, right? So what do we do now? Now to solve collision, we have some effective techniques which are called chaining and open addressing. So these two techniques again are asked in the interviews, and they are very easy. So see, let me explain this diagram first. So what happens is that you have a universe of keys. So this is the possibility of the keys, right? You can take it as a constraint. So if you want to store an array, and each element in the array can be from 0 to n, right? To any unlimited value, maybe. So then your universe of key becomes n, right? Every possible number from 0 to n. Now your actual keys are the actual values that you want to store. So it may be possible. See, it is not always the case that you get every single value that you have in your constraint, right? There is always a lesser or a handful of values that you work with, even though a larger number is possible. So the keys that you work with, they are called your actual keys, and all the possible values for your keys fall into the universe of keys. So now in the actual keys, suppose we have a key k4 which maps to an index of 1, right? After applying the hash function, it maps to an index of 1. Then we have another key 1, which similarly maps to the index 1, right? So now we have a collision because at this particular spot, two contenders are there, right? K4 and K1. So what we do in chaining is that in this table T, this hash table, what we do is we store pointers to a linked list. You have covered linked list in the first lecture, so I hope you know what a linked list is. So in this table, we make it an array of nodes, right? So this is storing nodes, and for each index in which we want to store a value, we point the hat to a node containing that value, right? So for storing K4, what we did, we made a node with the value K4 in it, right? And then we added it to the linked list. So we, in the index of 1, we added a pointer which pointed to this node. Then we had a value k1. So again, since there was already k4 at this index, what we did was we changed k1 to this particular index, right? So now it becomes a linked list. There is k1. And one thing to notice that you might think by default that every element would be added at the end, right? So it should be that K1 came first and then K4 came, but that is not the case because we want the insertion to be of a complexity constant complexity as well. So if you try to add it at the end, the complexity would become n, right? Or the length of the linked list. In the worst case, it could become all the keys. In the case that all the keys hash to the same index, then you would be storing all the keys in the same at the same index, right? In that case, insertion would take n times, right? The complexity would become n. So which is not what we want. So we insert every value at the head and not the tail of the linked list, right? So this again we are going to see in detail in the next slide. So in the next slide, we are going to see how each of these operations are performed in chaining, how insertion is done, how search is done, and how deletion is done. So I hope this concept of using an array of nodes of linked list is clear. So in this, the insertion, search, and delete are simple concepts, the same way that we do these for linked list. So suppose we wanted to insert in our hash map or a hash table t a value x, right? So x is our value and t is the hash table. Now we want to insert x. So we do, we insert x at the head of the list, right? So t is our array, and in this, at the head, we insert x, right? So see, this is what is done here. Now suppose there is another key x and we want to insert it, and after applying the hash function to the key of x, this h represents your hash function, right? So after applying the hash function, it can give you an index. It will give you an index. So suppose the index turns out to be 1. Now we want to store it at this particular place, right? So what would I do? I would store it somewhere here. I would make a new node, and then I would make this node point to the new node, and I would make the next pointer of the node point to this K1 node, right? So this is how I'm going to insert a new node in chaining, and this is how my collision is going to be resolved, right? And then for search, you do a simple search. First of all, you find out the index, right? So for that, you apply the hash function. After applying the hash function, you get the index in the table, in the hash table. And then when you get the index for that particular key, you can search in the list whether the element exists or not. If it does, then you can get the answer. Otherwise, you will reach the null pointer, and then you can say that the element does not exist in the hash table, right? And then deletion is again simple as deleting a node from your linked list. So you simply just find out the index using the hash function, and then you delete the element from that linked list. So this was it about chaining for resolving collisions. And now we have open addressing. So in open addressing, we do not have any extra data structure. We only use a single table, which is our hash table, to store all the elements, right? So what is the general idea of using open addressing? Suppose I have 79 stored here, right? And now there is another element which also hashes to the index 1, right? So now what I could do is, in chaining, I would make a new node to store that particular element. But in open addressing, we do probing, right? So what happens in probing is, let us take the example of linear probing. So what then I would do is, I would move to the next slot and see if it is free. If the next slot is free, then I would store the element in the next slot. Otherwise, I would check the subsequent slots. So the first empty slot that I encounter, I will store my element in that slot itself, right? So this is what happens in open addressing. But in linear addressing, we check every subsequent block. But there may be many other types of probing. There is also a double hashing. So there are many other ways which can be followed based on the type of open addressing that you are using to store the element. But the general idea is that after hitting a collision, you check for another empty position in the same hash table. So if there is an empty position, then you just add your element to that slot, right? So this is what happens in open addressing. And now let us look at how we do insertion and search in open addressing. So insertion is pretty easy. See, the only difference here is hash function now requires two parameters, right? So there is a parameter for key and there is a parameter I. So what I says is the number of collision. So let us do a dry run of this on this diagram. So initially my I is 0, right? And now in J, what I store is the mapping or the hash value of key K for when I is 0 or when there is no collision, right? So I get the value of J. Now suppose the index is 1, right? The index J comes out to be 1 for my key K. And since this position is already occupied, so I will have to move ahead. But if this position, the T of J was null, or it was empty, then what I would do is, I would store the value in that at that index, and then I would return the index, and I would return that particular index as my key, right? So this is what would happen if, in case there was no collision, you would just store, if suppose it came out to be 2, right? J came out to be 2, and since 2 is empty, I could store any value here, and then I would return 2 in the output saying this is my returned result, right? But in case there wasn't an empty value, in case T of J was not null, it had a value already sitting inside it. So what I would do is, I would increase the value of I, right? So now my I would become 1. And then for hash function, uh, taking in parameter same key K, and now I becomes 1, right? So for this, you could define a separate function. For example, when you take in 0, the hash function could simply be a mod function, right? So it could for I0, it could simply return uh, k mod 7, right? But for k comma 1, when your parameter changes, parameter I changes, you could have a different hash function. And the difference is also in the types that you have for probing. So for example, what one thing you could do is, you could do x plus 1 mod k, x plus 1 mod 7, right? So initially for my 0th step, my mod function was x mod 7. Now I could do x plus 1 mod 7. So that would check for the next subsequent index, right? So it would check for this particular value if it is empty or not, and so forth for the next values. Now when I find a empty slot, it would store the value there. Otherwise, it will keep checking until I reach the end of my table, right? So M is index M means the end of the table, right? So if I reach the end of the table, then I will quit and say the hash table has overflown because now there is no space to store the element. So this is what happens in while inserting elements in our hash table using open addressing. And then searching is again similar. So in search, what you do is you would first find, if you want to search a key k, then what you would do is you would apply the hash function. Since in the beginning there you assume there is no collision, right? So you take I to be 0 and then you keep searching. So suppose your index turns out to be 1, right? And then you check it at the element stored at first position. If this element is equal to the value that you are searching for, it's a success and you give out the index. Otherwise, you again increase the value of I, and then you would use the next hash function for the first collision when your I turns 1, right? So then you would use the next hash function, and then you can check whether the next position that comes in the next index that is given by the hash function is containing your desired key or not. And you keep checking this until either you find your value k or if you reach the end, right? So these are two general cases. Either you can find the value moving like this or you can reach the end of the list. Another thing that would happen is you could also reach an empty slot. So if you reach an empty slot, it also means that your key is not present in the table. Why? Because if it was present, it would be taking up some slot, right? It could have been stored in that empty slot if it was present. But since it is not present, there is an empty slot, right? So an empty slot or an overflow could end this algorithm, right? Or you could also end it in success getting the desired index. So this was how your theory part was for hashing, how what hashing are, what hash function is, what hash tables are, and then how we deal with collisions. So is there any doubt in this until now, moderators? All right, great. So now let us move on to the applications part. So since hashing is a quite complex concept to implement, however easier it may be to use, but it is quite complex to implement a hash table on one's own. So we are going to use some built-in functions for hash, and for that, C does not support hashing as of now. You will need to use your own hash table, which is why we are going to use Java for that purpose. But the concepts will remain same whether you are using Java or Python or any other OOPS language. Even if you try to make your own hash table in C, then also you can apply these logic to solve problems, right? So let us move ahead with Java. And now Java provides a class hash map, right? So hash map is the data structure or the class that you never knew you needed. It is that much useful for solving your CP problems or for solving any type of problems that you might arise. In my initial days of coding, I would be sitting down stuck on an arrays problem for days just because I did not know how to use hashing and that problem needed hashing. So there may be some problems which you might think that can be solved using arrays, can be solved using linked list or any other data structure. But if you use hashing, they are only a matter of minutes to be solved, right? So for that purpose, hash map is what Java has to offer. There is also hash tree and hash set, but we are going to focus on hash map because it allows us to store a value, a key value pair, right? So you can use it to store frequencies of elements, or you can use it to store the occurrences and so on, right? So This is the declaration of hash map in Java. You use the class name followed by the domains that you want. So in case you had a question which was asking you to find out the first string occurring twice or the most frequent string, so for that purpose you would need to store strings, right? So for that you can also use strings, you can use characters, long, double, any class that you want. But here in example this is integer, you can use any object that you want, right? And then you give the name. This name can be anything, new keyword to define a new hash map. And this is how you declare a hash map, easy. So then comes insertion. If you want to insert a key value pair, the syntax says write the name of your hash map. So my name is hash, I'm writing hash dot put key comma value, right? So first you write the key and then you write the value. So this is going to take of 1 on average. Now, this is saying on average, right? It is not always the case that insertion takes a time or a constant time for inserting in a hash map. And that is because sometimes maybe your hash table becomes full and then it needs to be resized. So, resizing is again another concept in hashing, but we are not going to cover that in detail. It simply means that your hash table is full and it needs to we need to increase its size, so then your hash table is resized. Generally it is doubled and then it takes more than a constant time to copy all the existing value in a new bigger table, right? So that is when your worst case happens, but otherwise it is pretty simple. It generally takes a constant time for insertion. Then comes your searching. So if you want to search for a key, whether a hash map contains your particular key k or not, there is a simple function get. There is a simple function contains key. So using contains key, you can get a boolean value to find whether the hash map contains this particular key or not. If you want to find and if it does contain the key, then you would want to find the value, then you can use the get function, right? So contains key is going to give you a boolean value, true or false, whether hash contains this key or not. If it does, then you use hash dot get k to find out the value stored at this particular key, right? How this exactly happens, you are going to understand better when we look at an example. And then let's come to deletion. So in deletion, it's really easy. You just need to use a remove function offered by hashmap, and in that you write the name of the key. So this is going to remove the pair. It is going to remove the key as well as the value to which the key is mapped, right? So this is going to remove the pair. And then there is the size function. So it is going to return the number of elements in your map, right? So hash dot size is going to return how many elements are stored in the hash. There are many other functions, and this is the link for documentation. This is a very good place to start learning new methods and learn how to use those. So if you want, you can anytime click on this link and go and read the documentation. Now we are going to learn two logics which you are going to use frequently while solving problems using hash maps, right? So the first one is storing the frequency using hash map. So suppose you have an array and in that it has a size of n, right? And then for each element you want to find out the frequency of that element. So how you do that? Now I have written a simple for loop which runs from index 0 to n of the array. And then for each element, we are checking whether hash contains that element or not, right? So array I will give us the element in the array at the given index. And then we will check whether the hash contains that element or not. If it does not contain the element, so this exclamation means not, right? So if hash does not contain this element, then what we do, we put this particular element with a value 1 because it is for its first occurrence, right? Otherwise, if this element was indeed in hash, already inside stored in our hash, then maybe this is not its first occurrence, it could be second occurrence or third or fourth, right? So for that purpose, what we do is we keep updating the this keys value every time we encounter it, right, in our array. So for example, we had an array with values with some numerical values 1 2 3 4 5, and then they were occurring frequently, right? So maybe there was 1 1 2 2, right? So for the first one, since hash is empty, when I is 0, hash is empty. So it is going to store the first occurrence, right? With the value as 1, which means it is occurring first time. Now, when 1 occurs second time in our array, this condition will turn to false. Why? Because hash already contains 1, right? So this is going to be true. And since we have exclamation here, it means it acts as not, like you have and or not, right? So it acts as not. Now this is going to turn out true in false, right? So now this condition turns to false. So it comes to this condition in the else part. And now we put 1 here, right? And then we do hash dot get array of 1, array of I, right? So what this is going to do is this is going to give us the existing number of occurrences of this element array of I, right? So since in 1, for its first occurrence we stored 1, right? Because it was its first occurrence. Now since it's occurring second time, when we do a hash dot get 1, we are going to get this value, right? We are going to get 1 here, and we add 1 for it because this is another occurrence. So we add 1 and now it becomes 2. So now the value of 1 is 2, which means the number 1 has occurred 2 times, right? So this is how you update the frequency each time you encounter an existing number, right? So this is going to give you the existing number of occurrences, and then you update it by 1 for every time you encounter it, right? So this is the way how you store your elements using hash map. And then there is traversing. So suppose you had stored all the frequencies and now you need to find out the frequency of each element, right? So each distinct element. So for that, there is an inbuilt function in hash class which is called key set. So when you use key set on hash, it is going to give you a set. A set is just like a mathematical set in which you have elements. So it is going to give you a set of all the keys that you have in your hash or hash table, right? So this way you will get all the keys, and then you can again use a for loop to find out each element in the set. And each element in the set is indeed it's actually a key in your hash, right? So now you can work on each element individually or in a linear fashion, right? So this way you will be able to traverse over the complete hash map, right? So this is a simple printing statement. Here you could also have comparisons, like if you wanted to find out the elements which are occurring 2 times or exactly 3 times, then you would want to know, you would want to compare that value and see if the value of hash, the value stored in hash at the key E is equals to 2 or 3 or whatever your question demands, right? So this is the basic printing. Now in this loop you could do whatever you want with the values of hash, in apart from updating it, right? So in this loop you cannot update the value stored in a hash, but you can only see it and store it in some element and use it, right? So you cannot update the hash at this point, only see it. So this was all about traversing in a hash map. And now let us discuss some questions quickly. So first question is, find whether an array is a subset of another array or not. Now, if you try to use an array for this, for solving this question, it would be an headache with loops and loops, right? And it would be at least a complexity of n square. If n is the size of your array, then it would at least have a complexity of n square, right? Even if you try to do some other algorithmic things. But with hash, you can do it within a complexity of a linear complexity, right? A complexity of n only. And how is that possible? See, we have an array 1 and we have an array 2, right? So what we do is we use a hash and we store all the elements of array 1 in the hash, right? So this is how you store all your elements in the hash. And then for array 2, we traverse in the array 2, and then for each element in array 2, we check whether that element belongs in hash or not, right? So if all the elements of array 2 are present in our hash, that means that all the elements of array 2 are also a part of array 1, are also present in array 1, right? So this is going to say that array 2 is indeed a subset of array 1. If there was a single element which was not present in hash, then this condition would be false, right? So we now have found an element in array 2 which is not in array 1. So array 2 cannot be a subset of array 1 now, right? So this is how we can use hash here. So essentially, we are using hash to check the presence and absence of keys in an array, right? So once we put down all the values of array 1 in hash, now checking for a value whether it is present in hash or not only takes a constant time, right? So this is the most powerful function of using hash, that you can check whether an element is present in it or not in a constant time, right? You cannot do so with other data structures. To check whether there is a key k in a linked list, you would have to traverse the complete linked list in the worst case, right? And for even if you are using trees or self balanced trees, it would take a complexity of at least n log n to find out whether this key exists in the tree or not, right? But with using a hash, you can find that out in a constant time, right? So this is the most powerful line that you can use in while applying hash map to this problem. So it's quite easy approach. Otherwise, if you were going to solve it using array, it was going to take a lot of time and complexity, right? So this was the first question. Now let us come to the second one, which is finding a pair with a given sum. So I guess most of you must have encountered this question somewhere while solving CP problems. It is a tricky question if you do not use hashing. So, but hashing makes it very easy. How? Let us see. See, the idea with this approach is that for the given array, what you do, you have a pair, you have a given sum, let's say k, and now you need to find for each element where the k minus the value of that element exists or not in the array, right? So if it does, then you have found a pair with sum equals to k. Otherwise, there isn't a pair with that element, right? So using hash, what we can do is see, this stamp here is storing sum. Sum is our required or given sum. It can be taken as a digit k. So sum minus the value of our current element, right? So this is the difference between sum and the existing value, the value at hand. So if we have this difference in our array, then we have a pair, because if the element having the value as this difference plus this existing element array of I is going to give us our required sum, right? So this is the logic, and how you apply it using hash map is that you can first store all the elements in your hash map, all the elements of array in the hash map, and then for each element of array you can check whether the difference between sum and the current element exists in the hash map or not, right? So then it would be really easy, because now you can check with a constant time of 1 whether the sum minus array I or sum minus the value at hand exists or not. If it does, then you have a pair with given sum. Otherwise, you don't, right? So this is the approach. And in this particular approach, what we did was that instead of storing the array first, we checked for each particular element whether the difference was present in hash or not. So since if we have a pair, then we are ultimately going to find out the one of the elements which has the difference, right? Which has the value of difference stored in the hash map. So this is again the same approach, only we need to do it in a single turn of traversing the array. But in any case, it is only going to take a time of n, right? And not a quadratic complexity. So otherwise, if you are not using hash, this would be a tricky problem to solve. And there may be questions like find a pair with given sum in BST instead of an array. And then you would also have to get your brains on for solving that question. But using hash, using this simple concept, you can do so very easily. So this was finding a pair with given sum. And now let us come to the next question. And the next question says check whether a subarray with sum 0 exists or not. Another variation of this question is to check whether a subarray with sum k or a given sum exists or not in an array, right? So you have an array and then you have sub arrays of an array, and you need to check whether any of the sub array of that array has a sum given sum or not, right? So the approach that you use to solve problem is using hash map. What you do is see if you keep storing the sum that you encounter with each element that you encounter in the array with this particular statement, right? So in a for loop you are storing the sum and while encountering each element in the hash, right? And if indeed the sum was zero for a particular sub array, your sum is going to remain same, right? At some point, your sum will become same. If there are two particular elements, let's say at index 4 and at index 10, and between them the sub array has a sum of 0, right? So for that purpose the sum of all elements until 4 and the sum of all elements until 10 is going to remain same. Why? Because all the elements between those two values add up to 0, right? So now it becomes is that simply if you find out a sum which already exists in your hash map, then it says that since we already have this particular sum existing in our hash, then this sum has occurred previously. And since both the sum are equal, then it must be the case that all the values between those two indexes add up to 0, right? So this is the approach that you use to solve this problem. Now, since we are using 0 here, we are directly checking for sum. If it was k here, then we could check for sum minus k to exist, right? So this was the approach that you use for solving this problem. And then we have two more problems. Now let us come to anagrams. So anagrams are again a special combination of characters which make up a string. So an anagram is a string. Anagram of a string is a string which has the same letters at that string, right? So act and cat are anagrams of each other. God and dog are anagrams of each other in the sense that they both contain the same characters, only their order is shuffled, right? So to solve this particular question in which we have an array of strings and we need to return groups of strings that are anagrams. So we have a array like this words array, and in the output what we want is a group in each line, a group of strings which are anagrams of each other, right? So how to go about this? So to solve this, what you can do is for each element of the array, for each string, you can sort it lexicographically, right? So sorting it lexicographically means the first letter, the smallest letter comes first, right? So it's like sorting it in the order of dictionary, in the order of alphabets in alphabetical table, right? So A comes before C and T comes after C, right? So to sort cat, you get act. So this is the lexicographical sorting of a string cat, right? And similarly, it will be same for act because C comes after A and T comes after C. For tag, it would become act because T comes after A and after C. So we would move T to the end, right? So this is just sorting the alphabets, sorting the characters alphabetically. After you do this, you would see that for anagrams, since we have the same characters but shuffled, after sorting, these anagrams would be identical strings, right? So after you sort this string lexicographically, you will get identical strings. Both of will these both strings will be sorted to DOG, right? Because D comes first, then O comes, and then G comes. So even this word is going to be sorted to the similar value, right? So all these three are also going to be sorted to the same value act. Right now, how we can use this is we can have a hash map, and while traversing over the complete array, string array, we can check for each element after sorting it whether it exists in our hash or not, right? So when we commit act, we find that our hash is empty. So we put it in our hash, right? And then we come to chord. So even this is going to be sorted to DOG, right? But our hash does not contain this particular element, right? So this we are going to add to our hash, and then we are going to move on. So now we come to cat, right? So cat is going to be sorted to ACT. And since hash already has act element in it, right? So we are only going to add cat to the list, right? Because see, in this approach, what we are going to do is if there is an element which is not present in our hash, we are creating a list, and then to this list we are adding that element, and we are putting it inside our hash, right? And the key will be the sorted string. So the sorted string becomes the key, and the value becomes our list of the strings which sort to the same string, right? So now, whenever you encounter a cat or tag or any anagram of act, we are going to keep adding it to the same list, right? So this is how we are going to solve anagrams problems using hash map. And then we have the last one, which is longest consecutive subsequence. So again, in this, what we need to say is that given an array of integers, we need to find out whether what is the length of the longest subsequence such that the elements in that subsequence are consecutive integers, right? So consecutive means 1 2 3 4 5, like in that subsequent order without skipping a letter, keeping an integer in between. So there can be a range of integers from maybe 6 to 12 in a subsequence, or it can be from 99 to let's say 105, right? It could be any subsequence. We do not know what it is. So the naive approach would be, or the brute force approach to solve this problem would be to sort the array, right? But since sorting is going to take a lot of time and complexity as well, it is easier to use a hash map. Now, how do you use a hash map to solve this problem? So, using hash map, see, you check for each element whether it is the starting point of a sequence or not. Starting point of a sequence means that if it does not have its previous or predecessor in the hash, then it means that this particular integer is not a part of a sequence. If it did have a predecessor in the hash, then it would be a part of a sequence, right? But so to check that condition, we put down it like array of I is our current element, and then we subtract 1 to get the predecessor, and then we check whether our hash contains that element or not. If it does not contain, then it is clear that this particular element, array of I, is the starting element of our sequence. It is a potential sequence which we can start using array of I. Now, to check whether or how long this particular sequence may be, what we do is we use hash. So what we do is we check for array of I, and then we keep adding 1 to it, right? So j is given a value of array of I, and then we keep incrementing j by 1 and checking for each value of j whether hash contains that key or not. If it does, then we are getting a subsequence because those values exist in our table. And if it does not, then that is the element which hash does not contain. So that is the element at which our subsequence breaks, right? So after, if we have an element which hash does not contain, so that is the point at which we do not have a consecutive sequence anymore. So we update the value of our result
by saying j minus array of I, right? So j is after incrementing until we find an element which is not present in the hash or which is the breaking point of our sequence. And then we subtract the value of array of I because we want to find out the length, the total length of our subsequence, right? So then we update the value of result using the max function. If the result is less than this particular length, then we update it to this, otherwise we keep it to result itself, right? So this we are going to do until the end of the array, until we reach the end of the array, and whatever result we have finally, it is going to be our answer, and we are going to return, right? So this is how you solve the longest consecutive subsequence problem using hash. And then of course you would want to know where to use hashing. So there may be like some problems in which arrays would be advantageous to use, some problems where you would rather use a bst or a linked list. So this article you can check out to find out where to use hash tables. So hash tables are generally not very advantageous to use in case of ranged queries or problems like sorting, or where you want to work with contiguous indices, right? Because in hash we prefer doing searching for an occurrence of an element, right? So that are the types of problem that you can solve using hashing. And this is the article which you can refer to, read some more details. And then for more practice questions, and in fact for practicing the questions that we just discussed, you can go to this particular link on Geeks for Geeks. It has a list of questions based on hashing. It has, I guess, 21 questions which are most frequently asked in any coding question, any coding test, right? So you can practice those questions. And again, there is a playlist for lead code at this link, which also you can visit. So this was it about hashing. And this is the book that I used to explain to you the theory concepts. You can go to this link and read the chapter if you want to get an idea, get a deeper idea of the things. And of course, you can go to GFG anytime to uh, find out more about it. So that was all from my side. And I thank you. And if you have any doubts, moderators, please let me know if there are any doubts.
I hope. Thank you, ma'am, for this session. I hope most of your queries regarding the DSA has been cleared by now. However, even if you're left with any kind of queries, please feel free to ask. You can either write your doubts in the chat box or you can raise your hand. We will unmute you. Anyone have any kind of doubt? Does anyone have any kind of doubt or shall we continue? You can write your doubts in the chat box or can raise your hand. Okay, so at the end of the session, we have organized a quiz for all you guys, and codes are there in the chat box. And if you have any kind of problem with that, just raise your hand. The link and the code is in the chat box. And if it is not accessible, please look into your WhatsApp groups. It is there too. And thank you, ma'am, for sparing your beneficial time for us and enlighten everybody today. Creators Garage is looking forward to having many more sessions like this with you in our upcoming events. And would also like to extend our thanks to all the participants for being such a great audience. Hope to see you all in our upcoming events too. Thank you. And please don't forget to go through the quiz and the feedback form. I request everybody to please join in for the quiz. It will start soon.